All right, great. Well, thank you so much for having me to speak here at this lovely conference. I'll be telling you about some work we've done over the past few years with Igor, with Silviu, who you both met, and Benjamin, who's in the audience, Benjamin Sogard, and Bernardo Zahn. And so I'll tell you about this work we've been doing to understand two-dimensional U1 gauge theories using the Hamiltonian lattice, which has been a popular theme already. So when it comes to 2D U1 gauge theories, this all starts with the Schwinger model. And this has been discussed a number of times already, so I won't belabor the motivation. But it's worth noting that Schwinger published this model in 1962. I was not born, my parents were not born, and yet it still commands enduring interest. And so, as you can see in the citation graph here for this paper, interest really picked up around 1973, and that's an important date for us. When QCD was recognized as the model of the strong interactions. And so the Schwinger model came to be seen as a really useful model of a solvable gauge theory where we have confinement. Confinement being the natural scenario in 2 dimensions with a linear Coulomb potential. And so, despite the fact that Schwinger's original model of a single massless Dirac fermion with a U1 gauge field is solvable, if you make little modifications, suddenly you have a non-trivial interacting quantum field theory. And so in particular, in 1976, Coleman studied the 2-flavor massive version of this model, which will be most of my focus today. And some questions were left unanswered. And so in particular, I want to focus on this question of what is the infrared behavior of the massive multi-flavor Schwinger model, and focusing on the 2-flavor case. So let me describe that problem in a bit more detail. So here is the Lagrangian for the model we're talking about. We have a U1 gauge field. We have this theta angle, which will correspond to a background electric field in 2 dimensions. And then we have several Dirac fermions coupled with various masses. And so our parameters are these masses and the theta angle. And we can ask then what is the phase diagram of this theory. And so you already saw this picture yesterday from Grisha, the 1-flavor case. I'll touch on that. But essentially, Grisha showed us that there's a critical mass at theta equals pi, and its corresponding negative mass at theta equals 0. If you ask about the 2-flavor case, well, one thing we know is from Schwinger and later papers where the massless case is solvable, and this was later understood to be an example of bosonization. And so through bosonization, we know what happens at the massless point. I'll talk about that in the next slide. And then at large masses, we have to degenerate back to this 1-flavor diagram if we integrate out that massive fermion. And so we sort of know what the wings are going to look like here with some c equals 1/2 lines. But as far as what happens in the small mass, strongly coupled region, but not at the massless point, well, that's not clear from either of these limits. And so the lattice is going to be our best hope to understand how to fill in that diagram and see what the full phase structure is. And so, one question we can ask is the lattice up to the task? Obviously, the answer is going to be yes, but I'll argue that it's not obviously so. There are some real struggles to make the lattice work in this region. And so as a first test of what the lattice can do, let's not throw it at the strongly interacting, non-trivial, unsolvable case. Let's throw it at this massless point and see if we can reproduce the known behavior from bosonization. So let me tell you what that is. So using bosonization, we can say that for when the number of flavors is at least 2, there's going to be an SU number of flavors, level 1, WZW model that describes the infrared of the massless theory. And so then we could ask, what does that mean for various observables? And I'll focus on the energy of the first excitation on the lattice, or in the continuum, either way. We would hope to see that when so to the right of this plot is a function of inverse length. So if I take a very small circle, we're still in the ultraviolet, the lowest state is going to be the Schwinger boson, which was shown long ago to have a mass of root NF over pi times the gauge coupling. So that's what should happen in a small circle. As we go to a large circle, we should enter this region where we're seeing the conformal theory. And so we should have a gap proportional to 1 over L. And the constant in front is related to the scaling dimension of the lowest operator in this WCW model. It's computable. It's 1 minus 1 over NF. So this is what we should expect to see if we just run our Hamiltonian lattice model, which I'll show you in the next slide, ask what the first excitation is, and plot it. So this has been said a couple of times, so I won't belabor it, but this Hamiltonian lattice model that we'll be using is to take our Dirac fermion, or several of them if we have many flavors, and stagger them on alternating sites. So one component will go on even sites, one will go on odd sites, and then we're going to have gauge fields along the links. So this is a picture I think many people are familiar with. I'll just leave it at that. And so with our operators laid out in this way, we can write down a Hamiltonian. And so what I've done here is said, okay, well, there's a gauge kinetic term. That's going to be replaced by a sum of these Ln operators, which are electric fields on links. So this is the gauge kinetic term of the continuum Hamiltonian discretized. There's a fermion kinetic term that lets the fermions move around in the lattice. So that becomes a hopping term like this. And then the subtle one, which we'll come to in a bit, is this mass term. But the first thing you'd say is just take the fermion mass term in the continuum, discretize it, and what you get is this alternating sign times the occupations of each site and in each flavor, multiplied by, for what I'll now call m. But if we take this model as written, and then we try to make the exact same plot I showed you on the previous slide, well, we do okay with the Schwinger boson in the small circle region. But that's not our goal, right? Our goal is to look at the large circle, look at the infrared, and see what the phase structure is there. And we see that the lattice is really not doing a good job there. And so we see that this energy is getting much larger than we hoped for it to be. Now, to be clear, this lattice model is not wrong. If you increase the number of sites at a fixed length, making your lattice finer and finer, and you carefully extrapolate these points, you will get them to eventually go down to these lines. But in the limit we sort of care the most about, right, where the length is becoming infinite, we see we want the gap to be 0, and actually we'll show that it's becoming infinity here. So if we want to converge to 0, infinity is a really rough place to start from. So we hope we can do better, and in fact we can. And to see how, one way to motivate this, let's look in detail at this regime where I fix the number of sites and then go to a really large lattice, so that this lattice spacing A is going to get quite large, and this gauge kinetic term is going to dominate. So let's look at this region, which is called the lattice strong coupling region. So if I take the Hamiltonian and I rescale by this g squared A parameter, I actually have a much simpler Hamiltonian, which I can exactly write down some eigenstates for. If I drop the small fermion kinetic term, which comes in an order 1 over A squared. So I'm going to just have the sum of the electric field energies, and then this mass term, where mu is the mass rescaled by that lattice spacing A. So we can ask, what is the ground state, or the ground states plural, of this strong coupling model? And one state that's obvious to write down is the state where all electric fields are 0. And because of the Gauss law on the lattice, which tells me that the electric field jumps from link to link by something related to the occupations of each site, the charge on each site, well, that actually, if you work out the Gauss law, fixes me into a single configuration of fermions, where my, say, odd sites are all filled, and my even sites are all empty. So there's going to be one ground state. If this is the lowest state, then it's unique, is what I'm saying. Now, you could ask, okay, what's the cost of taking one of these fermions and moving it to one of these neighbor empty sites? Well, if I work out the Gauss law, that's going to make the electric field non-zero on one link. So I'm going to pay a penalty for that in my first term. And then what happens for the mass term depends on the value of mu. You're also going to pay something positive times mu. It's going to be twice mu is the cost of that. And so if mu is at least -1/2, then this is costly. This will increase my energy. And so this thing ends up being the ground state when mu is greater than -1/2. However, if mu was less than or equal to -1/2, then the story changes. Then it becomes profitable to move those fermions around to other sites, creating electric field, paying some cost, but winning in the end because mu is sufficiently negative. And so in that regime, where mu is less than or equal to -1/2, I actually have many ground states. As you can see here, take this state, for instance. I could have, at each site, I could have filled either the first or the second flavor in the 2-flavor case. I should have said that this is all just a 2-flavor picture, just for fun. I could have filled either flavor, so there's going to be some degeneracy here in the ground state. That's what we would have liked to see if we wanted to get that gap to go down to 0. That would have been great. And so one could be extremely self-indulgent and just give it to ourselves. So what if we say, instead of working at this mu equals 0 to describe the massless theory, what if I shift the value of mu, and we can do it in a way proportional to the number of flavors, so that one flavor still lives in this gapped region where mu is greater than -1/2, and then I've carefully chosen this shift so that the 2-flavor case lands on the threshold where it becomes gapless, and from there on still gapless. So as I said, very self-indulgent, but it is something we're allowed to do. Because remember, mu is not just the mass, it's the mass rescaled by the lattice spacing. So what this constant shift in mu corresponds to is a shift in the mass proportional to the lattice spacing, something that will disappear in the continuum limit. So this does not change the continuum limit of your model, it simply shifts how you get there. It changes the convergence. And it does so in a dramatic way. And so it'll make a big difference on the lattice, as we'll see. This, what I've shown you, is not really the motivation. There's a much better way to argue for it, which is that when m equals 0 and we have an even number of flavors, doing this shift in the mass actually restores a discrete chiral symmetry that the lattice model contains that corresponds to a one-site translation, where all those upper components of the fermions become lower components and vice versa. So this is a part of the chiral symmetry, and it turns out when you work it out, to preserve it on the lattice, we showed in this paper from a few years ago, one should do precisely this shift. And so the fact that it can be motivated in this way for the massless multi-flavor model is a very happy coincidence, but this is really the ultimate motivation for making this mass shift. But let me now show you what this mass shift accomplishes for the problem at hand. So if I try to make that same plot from a few slides ago and now use the mass shift, we're doing a lot better. So first of all, we knew we were going to get to the right place here. We knew we were going to get to a gapless point when length becomes very large from the strong coupling limit. But not only do we hit that point, we also fall right along this line that, remember, corresponded to a scaling dimension of a WCW model with some SUNF group. And so we can see for one flavor, there's no CFT like this, and then as soon as we hit 2 flavors, we get this SU2 level 1 model. For 3 flavors, we get the right dimension for the SU3 level 1 model. And so we're really nicely reproducing the massless point of this theory. So that's great news. That's sort of one thing crossed off our list. We can reproduce that massless point. What about the NF equals 1 phase diagram? Of course, Grisha told you lots about this yesterday, so I won't spend much time on it. But I just want to go over sort of the methods we can use for that and how the mass shift influences it, because that will be important for the 2-flavor story I tell you next. So to briefly review what Grisha told you yesterday, so when theta equals pi, this means there's a background electric field of 1/2 on my spatial line. And so if m is sufficiently large, if it's costly to pair produce fermions that will change me from, say, electric field plus 1/2 to electric field minus 1/2, if that's costly, there's going to be 2 vacua. And so on this line out here, there's going to be 2 vacua, and charge conjugation symmetry will be broken. Now, there's going to be some critical point here, this m crit that Grisha was measuring yesterday. It's a 2D Ising phase transition where those 2 vacua merge, and then we have a single vacuum beyond that where those 2 electric field states are connected by pair creation. So we can ask, can we measure that? Of course, the answer is yes, but I'll show you what the mass shift does to help you measure that. And so what we see here, this is from our first paper on this mass shift, and we said, okay, well, there was this measurement of roughly this 0.3 or so value from a ways back without using the mass shift, and you can see as you take the lattice spacing to 0, it's converging linearly in the lattice spacing. Now with this linear shift of the mass proportional to the lattice spacing, what actually happens is if we do the same kind of calculation where we try to extract this critical mass and take the lattice spacing to 0, it's going to converge quadratically in the lattice spacing. So that's just a qualitative big improvement that will help us converge this number. And so what effectively happens is the mass shift more or less nets you 1 digit in this calculation. And so the first calculation was from the 80s. They had uncertainty in the 2nd digit. We repeated their exact same method and found uncertainty only in the 3rd digit. But of course, so this is all with exact diagonalization, which gets us to lattices of order of 10 to 20 sites, not large. There are these other fancier methods using tensor networks, matrix product states, DMRG, all these tools in our box. And that was, for a while, the best number, in uncertainty in the fourth digit. And then we had repeated this calculation using the mass shift and saw right away that, again, you get sort of one more digit. We could see that it was not 1/3. But then I'll quote instead the numbers we saw yesterday from Grisha's talk, getting us all the way down to uncertainty in the sixth digit. And another group did this recently as well, with a slightly different method. So long story short, you get another sort of slam dunk for this lattice model. We can not only find this phase diagram, it is now impressively possible to compute the critical mass to so many digits. So good. So let's move on now to the case we want to consider, the two-flavor phase diagram. So if we're given that this massless point is the C equals 1 CFT, the SU2 level 1 model, and then we've got these lines corresponding to the one-flavor phase diagram when one of the fermions is very massive, there's sort of three ways I could fill in the middle. You could say that this SU2 level 1 point is disconnected from the rest of the phase diagram. It's an isolated CFT. You could say there's a line of CFTs that goes between here. And this was suggested by Georgi doing some perturbative calculations around this massless point. It seemed like maybe perturbatively there was a line of CFTs going away from this massless point, which was interesting and got us thinking. The scenario I'll be proposing to you is a third scenario, wherein these lines of C equals 1/2 CFTs actually bend inwards towards the origin, which is not what you'd expect from semi-classics. From Coleman gave a semi-classical argument for a bending sort of outwards, like the scenario 1. But sort of surprisingly, they bend inwards, meet at the C equals 1 point as they come very, very, very close, but not quite touching anywhere else. So that's what I'll be claiming is the diagram. And let me show you some evidence from that, both from the lattice and the continuum. The title. Okay, so first some perturbative evidence. So if we take the mass of the second fermion very large, but not formally infinite, and try to integrate it out, we can ask how does that affect the critical mass that Grisha was showing you yesterday, this 1/3 value or so. And so one can do a calculation of how that large fermion is going to affect everything else. It's a calculation that's done in Peskin and Schroeder. One can read off some of these integrals, like 1/12 pi. But the story I'm telling you here is not so much about the quantitative number, so much as it is about the sign. The effective coupling, when I have this large mass, is going to be reduced relative to the one-flavor case. And so that means that if I measure this critical mass, it will actually be a little bit less than that 1/3 number. So that's consistent with this idea that these C equals 1/2 curves bend inwards towards the origin as we bring in the second fermion. So that's a nice indication that maybe the scenario 3 is correct. Now let's switch over to the lattice and ask ourselves an easy question we can do in the lattice. Let's compute the ground state for any set of masses and then ask what is the expectation value of the average electric field. So that's going to be an order parameter for charge conjugation breaking, right? If I have these two vacua with opposite electric fields, then the open boundary conditions I'm using are going to pick one, and I'll see that one happens to be the positive one. And so we're seeing that turning on in this region, just like what I was showing you, this sort of scenario 3, two curves merging here. And so this is another indication that maybe this is the story, that we have these two lines merging. But of course, it would be nice if we could do more than just see this order parameter. What if we could really map out the phase diagram and see where the critical points are point by point? And so that will be what we'll attempt to do next. So let me say a few words about locating critical points, about finite size scaling. Anna nicely mentioned that for me already. One way to extract these critical points, which I'll show you in the one flavor example, is to say that, okay, well, if I had a CFT on a line in the continuum, then I know what the entanglement entropy of some bisection of that line is going to look like. That this has been computed before very nicely in some work by Cardi and Calabrese. And they showed that there's this nice function of a log of a sine that gives you the form of this entanglement entropy as you vary that bisection point. So what you can do is try to compare the entanglement entropy on the lattice with this formula and sort of read off an estimated central charge for any given set of masses that you put in. Now, if we do this for the one flavor case where we expect a c equals 1/2 critical point, it's a little confusing at first because these curves go, they blow right past 1/2 and get up quite a bit higher. But really what we should be looking at is not the peak of these curves, but where they intersect, this sort of scale invariant point, where as I increase the number of sites, I'm not changing this estimated central charge. So this gives me a really strong estimate of where the critical point is. And it also gives me the estimate of the central charge. And we can see here that this is much closer to 1/2 and getting closer as we increase the number of sites. So this is one way, in general, if I have a one-parameter family of lattice theories, and there's a critical point among them in the continuum, this is one way of isolating it. And so we could use that in the two-flavor case by just scanning this diagram along a number of lines. And so this is the plot I want to spend some time on because lots goes into it. So what we've done here is on each vertical line, and then by some symmetry reflected into these horizontal lines as well, what we've done is made a plot just like the one on the previous slide, where for many different sizes of the lattice, we compute this estimated central charge, see where these estimated central charges intersect. They're always near 1/2, which is reassuring. And then extrapolate those points to the a equals 0 continuum limit. And that gives me these black dots, which are some uncertainty interval on where we think the critical point is for every value of say m1. So two great things we can notice. One is that they are nicely following the border of this kind of scenario 3 region where two lines are merging near the origin. And second, if I plot in white that perturbative line from before, that also beautifully matches up. So we're seeing excellent agreement with everything we expect from continuum analysis, and the lattice allows us to sort of extend farther and see that we're really getting merging quite close as we get towards m equals 0. I should say the background is just an example of one sort of plot of the entanglement entropy of these models. Many such plots go into making those black points, where I do many sizes of the lattice, many lattice spacings, finite size scaling, etc. But nicely in this case, you sort of see a nice outline of the region, even with just one lattice simulation. So this is what the lattice can do for us. It can really point clearly towards this scenario 3 phase diagram. And now with the last few minutes I have here, I just want to say a few words about going back to the continuum. What can we say about these two critical lines that are merging and getting ever so close as they come towards m equals 0? This is a really neat sort of picture, and we like to understand it a little bit better. So I won't be necessarily telegraphic about this, but what we can do is start at that m equals 0 point, and then use Bosanization, write our SU2 level 1 model, and then just try to go a little bit away from that point along the line m1 equals m2, which seems to be the super interesting line where I'm very close to two critical curves. And so what you can see is if you write this bosanized action here, is going to be, okay, so two bosons. One is this phi plus, that's our Schwinger boson. It has that mass √2/pi times the gauge coupling, so that's this term here. Then we have this other combination of the two bosons. We get phi minus, which does not, at leading order, have a mass. And then we can look at just subsequent terms and see what happens. And so you can see, okay, if phi plus is near 0, if phi plus is near 0, then as long as cosine minus theta over 2 is not 0, we're going to turn on this O minus operator. O minus is a relevant deformation. The CFT, it has dimension 1/2. And so if we turn it on, we're not going to get the sort of interesting physics we're looking for. But of course, if I tune theta to pi, then that does not happen. And so I have to work harder to see what's going to happen as I move away from that point. And so, so indeed, if this, if this O plus piece vanishes, then we're going to have to go to this second order piece and work harder to see what's deforming the CFT. And I'll just say that what happens is that it's going to be a marginally relevant operator that's deforming CFT, and it triggers a BKT flow, this famous Berezensky-Koster-Lasulis transition. And the RG equations for this Sine-Gordon sort of manifestation of this transition were worked out long ago in the 80s, There are sort of two parameters, one for the coefficient of this kinetic term and one for the coefficient of the cosine term. And they worked out all the RG equations very, very beautifully. One just has to figure out which trajectory on this plot we're on. The nice thing is the SU2 flavor symmetry of this model actually restricts us to be on only one curve on this diagonal curve, and then we're on the left side on this plot. And so it's actually straightforward to read off from this old work what our RG equations are for this model, and one can see what the beta function for our effective mass is here, and integrate this beta function to try to figure out what the mass scale is for this theory along this very special line. And so what we find at the end of the day is that the energy gap along that line is going to be e to the minus g squared over m squared. And so when we're very close to zero, right, this is a vanishingly small gap, but not zero. And so if you remember that scenario 2 that Howard Georgi had suggested before, it was as close as it could be to being correct. Perturbatively to all orders, it was correct, not just to the however many orders he computed. But nevertheless, what we find here is that actually there's going to be two c equals 1/2 lines that are ever so close, but not quite touching. And along exactly m1 equals m2, we're not quite conformal, but ever so close. And so many other quantities scale with this exponentially small parameter. This is really a neat example of something that also happens in QCD, where we have this dimensionless parameter alpha strong, and then all of a sudden we have a dimensionful parameter lambda QCD. Is a similar example where we're generating this dimensionful parameter out of the dimensionless m over g. And so charge conjugation is broken, and we're seeing this BKT flow. One last thing I'll say from the lattice, measuring this ridiculously small energy gap is going to be ridiculously hard. However, one could take the inverse of it and look for the correlation length on the lattice. And one can probe that correlation length by looking at, again, that estimated central charge on the lattice and seeing, if I'm not at a conformal point, okay, fine. How big do I have to make my lattice before I start to see that it's not a conformal point? That gives me an estimation of what the correlation length is. And so we can make this plot comparing the correlation length, the log of the correlation length as a function of g squared over m squared. And so there's a ceiling on this plot, and that ceiling is how big of a lattice I can simulate. But below that ceiling, I can try to say what this correlation length is as a function of this inverse mass squared. And then in the dashed lines, I've plotted the slope that we predict from the previous slide. And it seems as we decrease the lattice spacing to match up better and better. So it's a really beautiful example of seeing this kind of really neat phase diagram and probing it with some precision on the lattice. So I'll wrap up there. The main ideas here is that this mass shift, which has been mentioned a few times in this conference already, is a really powerful tool for looking at U1 gauge theories on the Hamiltonian lattice. It really enables a lot of calculations that would not have been possible otherwise. And in particular, we were able to use it to find this rich phase diagram for the two-flavor Schwinger model, seeing this manifestation of BKT flow. We can do lots more. We can do real-time dynamics. I have an example if anyone wants to see. We can do non-abelian theories. Sylvia told you about that yesterday. Three-flavor physics, which is an interesting case to explore farther in this model. Also a possibility. There's much more to do, but I'll stop there. Thank you.
Yeah, thanks a lot for a great talk. Questions?
Thanks, John here.
I was wondering, are you not losing a little bit of generality in your phase diagram by only studying real masses? I guess you can absorb one angle into the theta angle, but...
That's a very fair point. Yeah, absolutely. We could, right. With the one flavor case, one could take the phase of the mass into the theta angle. With two flavors, one could put a relative phase between the two masses. We have not studied that, but that would be neat to explore.
Maybe something will happen.
Yeah, maybe. I can't have no intuition, but I would love to see.
But I guess the BKT line will still sit at real masses and theta equal pi, because you need to cancel this leading relevant operator, and that takes some tuning. More questions? Yeah, Yuya.
Yeah, so it's very interesting to see that effective central charge follows the curve very nicely. And so if we, for example, consider CP1 sigma model at theta equal pi, then it is the opposite side of the JJ bar deformation of SU2 level 1 S Witten. So in that case, how would it behave, and how can we see the difference of generating mass gap between this dimensional transmutation and...
Interesting. Yeah, I'm not sure what happens in that model. You say it's a different deformation of this.
Opposite side of JJ.
I see. Yeah, I'm not sure, but we should talk further.
Yeah, maybe looking at it would be interesting.
Yeah.
So are you saying that it will flow towards the... So it approaches the conformal point. Yeah, the problem with that is that it's hard to simulate it in a UV complete, harder to simulate. Yeah, the great thing about this model is that you have a completely finite field theory into which this dimensional transmutation turns out to be embedded. My understanding is that I don't know this literature well, but people did simulate it numerically, no? Some spin model or some. Yeah, of course. But you need theta equal pi, right? Which is maybe more tricky. Yes.
Could you say a little more about the real-time dynamics that you've done?
Thank you for asking. Sure. Let me. Good. So So let me say something broadly before I show you this plot. So with either exact diagonalization or these matrix product states, one has very nice algorithms for taking this Hamiltonian, exponentiating it, and seeing what the time evolution of some state looks like. And so one thing one can do, just as an example, is take the massless theory, in massless one flavor model, where we know all the answers from bosonization, and say, okay, let me take my ground state, act with a Wilson loop at time 0, evolve it for some time t, and then act with what should have been a conjugate Wilson loop, but I missed the conjugate. That's a W dagger. And then see what this looks like as a function of time. And so if you do this with both the mass shift and without the mass shift, well, that's coming out more slowly than I expected. So it's going to be very suspenseful. But as we'll develop, the mass shift becomes increasingly important. And so yet again, we see it's important to be at this point with, at the special point of the lattice model in order to follow the continuum theory precisely. So okay, now we're starting to see it. You really want the mass shift, and in particular, note that this is a log plot. So these red points are really not doing great at this point. But with the mass shift, we have pretty great fidelity for long times, and so one can see reproducing the correct. In this free theory, right, everything's going to be periodic. One can see this period reproduced nicely, related to the mass gap. Lots of things come out from this. So I think there's lots more to study with this, but. We can do these things and explore some neat time domain physics, which is a great advantage of the Hamiltonian approach relative to other lattice approaches, to be able to just plug and chug this relatively easily. Thanks for asking.
Well, that's great. Maybe it's a great place to end this talk. Yeah, let's thank Russ again.